Okay, in this part we are going to address the solution for the specified problem. The algorithm used for the learning for the specified classification problem is ERT algorithm, and we are going to uh, discuss how we can use ERT in distributed fashion. And for knowing about ERT, we need to first know about decision trees, score and information gain, and ensemble learning and voting. Since ERT is a tree-based algorithm, we need to know about decision trees and score and information gain. And since it is an ensemble learning method, we need to know a little about ensemble learning and voting. So here is an example of a decision tree. In decision tree, we have decision nodes like this one and leaves, which would be our prediction with the decision tree. And in decision nodes, we have one attribute and one value which we compare the value in that attribute with that value or a splitting point. I'm going to go through the example here. So if you consider the first the first record, we check the value for the attribute 1 of the first record. Since it is not no, we go to the no branch, and there will be another decision node after that. We check the attribute tree in regard to the decision in the splitting point, and since it is equal to true, then we would predict B for this record. For the second record, we compare the first attribute with true, and it was the answer was yes, and then the predicted class was A. And for the third one, the value of the attribute 1 was true, so we go to branch yes, and then the predicted value would be A. If those were categorical attributes, if we have numerical attributes, we can have a splitting point like here in 50, and we can check if the value in that attribute is greater or less than this splitting point here 50, and if it was greater, we go to yes branch, otherwise we go to the no branch. When we want to build a decision tree, we need to come up with good decision nodes. Every decision node have one attribute and one splitting point, and we need to choose the best among the options that we have. So finally we choose the decision node with the highest score. Information gain is one of those scoring measures that I'm going to explain here with two examples. The left-hand side here is the data table, and the right-hand side is the visualization of that data table. Here I provided 4 discriminator lines. You can consider each discriminator line as a decision node, which classifies the space into yes and no branch. And you can see here that the best option among these 4 discriminator lines or 4 decision nodes would be the 4th one. And the reason for that is that the purity of the data after the purity of the labels after classification is higher in regard to other options. And the purity, you can consider the purity as the probability of one label in each class. When you can see that before classification, the labels were not so pure. After classification, you can see that the labels are pure. You can see that the probability here for the blue one is equal to the orange one, and after classification in the gray side, the probability of orange one is 1, the probability of blue one is 0, and in the green side, the probability of blue one is 1, and the probability of orange one is 0. You can see that the purity is good here after is good in each branch. Here is is another example. This would be our data, and this would be our options or the decision nodes that we have, and we want to choose the best one among these two. So we need to first classify the labels, the records with these two decision nodes. After classification, we have these results. If we replace each record with its label, we have something like this. So now you can probably see that the left-hand side decision node would be a better option, and we are going to prove this. So you can see that in the yes branch we have only 2 B's. In the no branch we have only A's, but here we have only B, but here we have 2 A's and 1 B. So here it's not so pure. So we can if we want to check how much pure is something, we can calculate the impurity, and if something is less impure, so we can consider it as more pure. So we have measures for impurity like entropy and Gini index. We can use them as our impurity measures, and we can finally we calculate the information gain based on these two impurity measures. And for calculating the information gain, first we need to calculate the impurity of all the labels for all the data records. And then we calculate the impurity of labels for the records after classification. And finally, we deduct the calculated impurities in the second step from the calculated impurity in the first step. Here is the example. You can see that the impurity of this one, or entropy of this one, is 1, but after classification we have 2 B's in the yes branch and 2 A's in the no branch, and if we calculate the entropy for these, we will have 0 for this one and 0 for this one. And since half of the data records fall into yes branch, we have half as the proportion of this side, and since half of the data is in the no branch, we have half as the proportion for the no branch. So we deduct the entropies of these branches, of the labels of these branches in regard to their with respect to their proportion from the entropy of all the classes, and finally we come up with the score, here the information gain. For building a decision tree, we need to start with the root, and for choosing a decision node for the root, we need to first have several options for the decision node. These options are generated based on the learning algorithm that we want to follow. For instance, if we are going to implement the IDTRY algorithm, we need to generate decision trees, decision nodes, as many as the attributes that we have on the data. And for the root, we will use all the data records that we have on the data set. And after after choosing the uh, decision node with the highest score or highest information gain, we split the data into two branches, the data records. And if all the labels for the data records in one branch are the same, then we will have a leaf uh, with uh, with that label. For instance, if all of the labels are A, after splitting or classification with the decision node, we would put A as a leaf at the end of that branch. And if we want to, if we split the data and the label are not the same, we can continue the process for the learning, and we can put other decision nodes on every branch. So, but for the data that we consider for choosing the best decision node is now the data after classification. You know, in the last step, for instance, data records 1, 2, and 5 fall in the left branch, and we only use these records for choosing a decision node, the best decision node on the left branch. And we do the same thing for the right branch as well. So we continue this process until we reach to the leaves, and sometimes we can have some uh, uh, ending conditions for this process in the algorithm. So in ensemble learning, instead of one decision tree, we learn several decision trees, and the number of these decision trees can be identified by the user. And these decision trees should not be perfect decision trees. They can be only decision trees that can predict better than better than random. So, and also these, if these decision trees overfit, uh, the whole decision tree results will not overfit. In the model that the general model that include all the decision trees may not overfit. So it would be safe that we have every one of these decision trees overfitted on the data. And after learning those decision trees, for application of them and for prediction, we need to have the voting process. So for instance, if we had learned 5 trees, and when a new data comes and we need to predict it, we need to predict with every one of those trees. And the final prediction of the whole uh, uh, ensemble learning method will be the label that the majority of the trees predicted. For instance, here, 4 trees voted for A, and 1 tree voted for B. So the final prediction would be A. So what is ERT algorithm? ERT algorithm is a tree-based ensemble learning method for supervised classification and regression problems. And we explained the important concepts that was needed for this algorithm, for learning this algorithm earlier. So uh, we can just briefly uh, talk about the difference and the difference of this algorithm. So we need several decision trees here instead of one, because it is an ensemble learning method, and because it is tree based, we will have decision trees. And for making the decision trees, we basically go through the same process explained earlier, and but for the options that we have for the decision nodes, we will have a different procedure for producing them. So we generate those options randomly, actually. Uh, the, the number of those options is a parameter that can be tuned by the user of the algorithm, and this number can be less than the number of the attributes that we have in the data. For instance, if we have 4 attributes, we can have 2 options. And for every option, we need to choose one of the attributes available. Uh, and for every attribute, we need a splitting point, and that splitting point is also chosen randomly. Here is an example. For instance, this would be our data. We have 4 attributes here, and we have the classes here. And we need to decide how many decision node options we want in the algorithm. For instance, we decided that we need only 2 options that we want to choose among them at every step. And for every option, we need to choose one of the attributes randomly. So for instance, here we chose attribute 1 and attribute 3. And for every of these options, we need a splitting point. And for the option 1, for instance, it was a numerical attribute, and we chose this number randomly as the splitting point. And for the other one, it was a categorical attribute, and we chose this category randomly as the splitting point. And finally, we would have 2 options like this. Option 1, attribute 1 is greater than 3.56, yes or no. And the other option, attribute 3, is true, yes or no. So at every step that we need some options for choosing the best one among them. We generate the options like this randomly. Now I'm going to explain the distributed ERT, which is the application of ERT algorithm for supervised classification problems when the data is horizontally partitioned. And based on the characteristics of the ERT algorithm, it would be possible to apply this algorithm when the data is horizontally partitioned, and I'm going to show this. So in distributed ERT, the data is distributed on different sources, and each source which has part of the data, it is several records of the data, is called, it can be called computing node, or it's a party. And computing node should not be confused with the decision node. These are 2 different things. Computing node can be a server in a hospital which holds part of the data. It is part of the records in the data set, and or it can be a phone which have which which have which has part of the data. And in, in this problem, we are going to address the horizontally partitioned data. So every party or computing node holds several records, a portion of the training data. And in addition to the parties which hold the data, there would be a server or a center which tries to learn a classifier based on the training data exist on those computational nodes or those parties. And we try to use the ERT algorithm, and those parties do not want to share the data with the server. They don't want to send all the raw data to the server. So we want to, what we need is decision nodes on every party, and every party will classify its records based on that decision nodes. And after classification, it will have two sets of records, and it replaces those sets with the labels of those records, and then sends two sets of labels, one for the right branch and one for the left branch, for every decision node to the server. And the center will receive this information. It will receive two sets, one containing the labels of the records that was classified in the right branch, and one the labels of the records that was classified in the left branch for every decision node from every party. And I'm going to explain this through an example in the following slides. Now we want to go through the example for the distributed ERT. Suppose that these three records exist on the computational node 1 or party 1, and these two records are stored on computational node 2 and party 2 or party 2, and we want to use ERT algorithm to learn a classifier from all these training data, all these 5 records. So these are our two parties or computational nodes which hold the data, and this would be our server which is interested in learning a classifier based on the data exists on these two parties. And we want to use the ERT algorithm for learning. One simple way would be sending all the raw data to the server. So after that, the server will have all the data and will learn the classifier based on the ERT algorithm from the data. But the server will have access to all the values for attributes for all the records. And we are not interested in this because due to the privacy concerns, sometimes the parties or computational nodes are not interested in sharing all the raw data to the server. So we need to learn the data somehow without sharing these values with the server or other parties. So we want to learn the trees without sharing the data, and for learning based on ERT algorithm, uh, we need to set some parameters before starting the process. First, we need to know how many trees we want to learn, how many decision trees we want to learn. Here, we decided that we want, for example, 2 trees. So the other parameter would be the number of options that we have uh, at every step for choosing the best decision node. So we need 2 random decision nodes, 2 randomly generated decision nodes at every step, and we will select one between them. And there is another parameter here that we need to set is seed, uh, which is the seed for the random function. And I'm going to explain why this is needed for us. So when we want to start for choosing the best decision node for the route, first we need the options on every party, including the server or center. When we have the same seed, when we set the same seed for the random function on every party, then they will generate the same random numbers, the same string of random numbers for us. So when we want to randomly generate these nodes, they will randomly uh, generate some nodes on every party, and those nodes would be the same on every party because we used the same seed, we set the same seed on every party, including the server. So here is an example. You can go ahead and do it by yourself. I did it on Python. So I set the seed 2020, and when I randomly generated the numbers were like this. For instance, we want for each of the options we want one attribute among the 4 available attributes that we have. Here, for instance, we came out the attributes came out to be attribute 2 and attribute 4. And then we need 2 splitting points for one splitting point for each of these attributes. For the first one, we randomly generated the splitting point. It was female or F. And for the second one, the randomly generated number, it was in the range of attribute 4. It was 74.22. So these are our randomly generated splitting points, and these are our randomly generated attribute indexes. So every computational node and the server would generate the same thing, and these numbers will make our decision node options. So every computational node and the server will have a copy of the options for the decision node. After having the decision node options for the root node on every party, we classify the data on every party with each of these options that we have. And for instance, for computational node 1, after classification of data records 1, 2, 3 with these 2 options, we would have such results. This is for option 1 and this is for option 2. And when we replace the labels of those records after classification, we would have something like this. We do the same process on computational node 2 with its own data, and we will have such results. Finally, we would share the labels after classification for each of these decision node options with the server. You can see that for this decision node on computation on node 1, we would have these two vectors. And for decision node option 1 on computation on node 2, we would have these two vectors. And the same thing for the decision node option 2. And these computational nodes will share this information with the server. So the server concatenates these vectors for each decision node. For instance, for this decision node, it will has BAA for the yes vector and no, AB for the no vector. And for this option, it will have AA for the yes vector and BBA for the no vector. And after that, the server, after receiving all this information, the server can calculate the information gain for each of these decision nodes. And finally, based on these information gains, which is the score for our decision node options, we would choose the best one, which has the highest information gain. Here, we choose this option, option 2. So after that, we can see that the labels in the yes branch are the same. So we do not need another decision node in the yes branch. So we will put a leaf here, and the label here would be the same as the majority, which is A. We can have another decision node in the no branch. And we need to do the same process for choosing this decision node. So the server asks for the same process for the no branch and send a request to those parties, those computational nodes. Those computational nodes and the server will generate two other decision node options randomly. And since the seed was the same, the options would be the same on every party. So we need to calculate the score for each of these decision node options and choose the best one. So as you can see, we do not use all the data anymore. We use the data that was classified in the no branch with the selected decision node for the root. So record number 2, 3 on computation on node 1 was on the no branch for the selected decision node, and record number 5 was on the no branch on the computational node 2 for the decision node for the roots decision node. So we use this data and we classify them with the options that we have. Then again, we will have two vectors on the server finally for the yes and for the no, and then we calculate the information gain and choose the best one. And we do the process until the end of the tree. So after do these processes, we will have one decision tree. And we need to, this would be our decision tree one. So since we selected to have two decision trees for our classifier, so we need to do the same process from the beginning for another decision tree. And after learning the other one, we will have two decision trees, and we will use this, which is learned based on the raw training data and without sharing the raw training data to the server or other parties. And we will use these decision trees to classify our test data.